Okay, another common way to prepare alcohols is to use what's called a Grignard reagent. And a French chemist named Victor Grignard won the Nobel Prize in 1912 for the development of this reaction. Now you might be thinking, wow, 1912 is when he won the Nobel Prize. Okay, Nobel Prize in 1912. However, this reaction is so useful that I guarantee you it's being done by somebody in this state somewhere right now. It's a very, very important reaction in organic chemistry. All right, it says here the Grignard reagents are often used to make alcohols. And to form a Grignard reagent, we take an alkyl halide. So here we have an alkyl halide. And the X, it can be chlorine, bromine, or iodine. It can't be fluorine. And then you treat that with magnesium metal. And the magnesium actually inserts itself in between the R group and the halogen. So it actually squeezes itself in between those two. Well, what happens is, let's say you take this molecule here, this is bromobenzene, and you treat it with magnesium. You make this reagent, which you call phenyl magnesium bromide, right? Because benzene, when it's a substituent, we call it a phenyl. So this would be phenyl magnesium bromide is what you would call this, phenyl magnesium bromide. You could abbreviate it PHMGBr like this. That would just be an abbreviation of it. The next one, that would be propyl magnesium chloride. This one here would be propyl magnesium, run out of space here, chloride, right? And you can abbreviate that just PRMgCl. So we like to use shorthands for Grignard reagents sometimes. Now, something you might notice here is that you have a bond between a carbon and a magnesium. Well, the electronegativity difference between carbon and magnesium is what? It would be 1.2, right? If you calculate the difference in electronegativity, you have 2.5 minus 1.3. So that's 1.2. And if you remember from Organic Chemistry 1, we said that up to a difference in electronegativity of 1.7, that was considered a polar covalent bond. And anything above that was considered ionic. But something else that we discussed in Organic Chemistry 1 is that the whole concept of a nonpolar, polar covalent, and an ionic bond, you have to take those numbers with a grain of salt when we compare the difference in electronegativity between atoms. And so this bond, the bond between the carbon and the magnesium, has significant or enough ionic character that we will actually treat it as if it's ionic. Okay, so we're going to treat it like these ions that we have in the yellow circle here. So essentially what you're making is a carbon anion or a carbanion, which can behave as a strong nucleophile or as a strong base depending on the situation. So let me show you how a Grignard reagent would work. If we have our carbon that we can consider like a carbanion, okay, so you have your carbon with a negative charge, and again, that's how we're going to treat our Grignard reagents. Well, if that's got a negative charge and you treat it with a carbonyl compound, you've got a strong dipole here, and so the lone pair on the Grignard reagent is going to attack that electrophilic carbon to produce an alkoxide. So what you do in the second step is you treat that with water, and that does a proton transfer to produce an alcohol. So what are you doing? You're taking a carbonyl compound like a ketone that's shown here. You're treating it with the Grignard reagent. And again, the R group can vary, right? It could be a methyl group, it could be an ethyl group, it could be a phenyl group, it could be a propyl group, it could be an isopropyl, and we'll see several Grignard reagents, but we still call this a generic Grignard reagent, which again would act as a nucleophile towards that electrophilic carbon of the carbonyl. And then in the second step, you add water to produce what? To produce an alcohol. Now you notice that I highlighted something here in red, that you're making a new carbon-carbon bond, right? This bond is a new carbon-carbon bond. And if you want to know the most surefire way, or one of the most surefire ways to gain notoriety in the organic chemistry community, and I'm sure you all want to do that, it would be to develop a new way to make carbon-carbon bonds. If you can find a new way to make carbon-carbon bonds in organic chemistry, you will be famous. You know, we see a lot of carbon-carbon bonds in a lot of different molecules. However, something that we take for granted is that making carbon-carbon bonds is actually pretty difficult. It's a pretty difficult thing to do. And that's why the Grignard reaction is still widely used and why it is such a powerful tool for an organic chemist. But remember, since you have a carbanion, it can behave as a strong base as well. So not only can it behave as a nucleophile, but it's also a strong base. And so when you're doing a Grignard reaction, right, let's say you're doing this reaction right here, you want to make sure that you're doing that reaction in anhydrous conditions. So anhydrous, okay, the first step. What does that mean? That means that you have no water, because even if you have some moisture from the atmosphere, what's going to happen is that your Grignard reagent is going to behave as a base, and it's going to react with the water, and it's just going to deprotonate the water to produce, in this case, it's showing an alkane. If you compare the relative acidity of water, which is your acid in this case, and you compare that to the conjugate acid over here, remember that the equilibrium will lie to the side of the weaker acid. Since we have a huge difference in pKa, we have a difference of around 10 to the power of 34. So since this is so a much weaker acid, the equilibrium basically shifts entirely to the products. And so if you have any water in your reaction mixture, it will destroy your Grignard reagent. Your reaction will be over. Okay, good night reaction. And so when we do Grignard reactions, they're usually done in anhydrous ethers in order for us to avoid having water in our reaction mixture. Common anhydrous ethers that are used would be diethyl ether, is used quite a bit, and also tetrahydrofuran. So this one here is THF, or tetrahydrofuran. This one over here is just diethyl ether, or ethyl ether, same thing. All right, there you go. So here are some examples of Grignard reactions. Let's say we were to take this molecule here. This is called cyclohexanone. And if we were to treat that with methyl magnesium bromide, sometimes we would call that a methyl Grignard, right? If we were to treat that with methyl magnesium bromide, I'm not going to draw the entire mechanism, but we can treat that methyl as if it's a carbanion, and then that's going to behave as a nucleophile, and the carbonyl carbon will behave as our electrophile. So that would be the first step of the reaction. We produce an alkoxide, which gets protonated after we add water in the second step. Let's say we have an aldehyde. Okay, if we have an aldehyde, the same kind of rationale applies. If we treat it with a methyl magnesium bromide, or a methyl Grignard, if you want to call it that. Okay, same thing here. Okay, we have our carbanion, and that's going to do a nucleophilic attack. Okay, and then in the second step, you add water and you make an alcohol. Well, what do I notice here? I notice that you go from a ketone to a secondary alcohol when you treat it with a Grignard reagent. You go from an aldehyde to a primary alcohol, or sorry, did I say a secondary alcohol? Because I meant a tertiary alcohol. My mistake. So you go from a ketone to a tertiary alcohol, an aldehyde, sorry, to a secondary alcohol. And you can also do a Grignard reaction on an ester. So here we have an ester. And you also make a tertiary alcohol when you do a Grignard reaction with an ester. The difference is that when you do a Grignard reaction with an ester, you have to use excess of the Grignard reagent followed by the addition of water. If we look at the mechanism for the reduction of, if we look at the mechanism for the Grignard reaction with an ester, you'll see why we need to add a second equivalent of the Grignard reagent. That's covered in our textbook. I don't have it in the slides, but I expect you to take a look at it. And so you need to know all of the reactions that are on here. So know reactions, and you need to know their mechanisms as well. All right, very important chemistry, Grignard chemistry. Well, what's the best way to memorize or to master Grignard chemistry would be to try some practice problems. The first question that I want to take a look at is question 1213. It says, how would you use a Grignard reaction to prepare each of the compounds shown below? Well, I'm going to move over to a blank document just so I have enough room to tackle this. Let me see here. There we go. Let's find some blank space here. Some Taylor Swift blank space. So this is 1213, and we're going to start with B is the first one. That's not a letter B, is it? There we go. B. So we want to make a tertiary alcohol. Okay. There we go. We want to make this alcohol. Well, there's actually two different ways that I could make this alcohol. Let me show you what I mean. So if I copy it and I put it down here, there we go. So either way, we're making a tertiary alcohol, right? So what did we say on the previous slide? Our starting material is going to be a ketone. Well, if I was to add methyl Grignard, right? If I was to think in terms of retrosynthesis, and if I wanted to use methyl magnesium bromide as my nucleophile, that would mean I'd be adding one of these methyl groups, either this one or this one. It's not important which one I'd be adding. And so what would be my starting material? I'd want to have 1, 2, 3, 4, 5 carbons, and I'd want to have my carbonyl like this. So I'd start with this molecule, which is called 2-pentanone. The name is unimportant right now, but I would start with this molecule, and in the first step, I would treat it with methyl magnesium bromide, and then in the second step, I would add water, and that would give me the tertiary alcohol. So I'd end up adding, that second methyl group. I'll just leave it as a bond line structure. Conversely, what if I, instead of using methyl magnesium bromide, what if I added all 3 of these carbons here? Well, for that, I would need propyl magnesium bromide. So 1, 2, 3 carbons, and then I'll put MgBr like this. Okay, well, what would my starting ketone be then? It would only have 3 carbons in it, wouldn't it? I have 1, 2, 3, and I'm adding 1, 2, 3, right? So I would start out with propanone or acetone. If I start with acetone, then I would treat it with propyl magnesium bromide in the first step. And then in the second step, I would treat it with water, and I would end up with the exact same molecule. There you go. So those are 2 different ways to make that tertiary alcohol. I could either start with this ketone and treat it with methyl magnesium bromide or methyl Grignard, or I could start with this ketone and I could treat it with propyl magnesium bromide. Let's try another one. Let's try C. In this one, we want to make a primary alcohol. So if I want to make a primary alcohol, if I think about this in terms of retrosynthesis, I'm going to want to start with an aldehyde. Well, all I have on here are 2 hydrogens, and I'm not going to make a Grignard out of just a hydrogen. So the only thing I could do is to use this carbon chain over here. So I'm going to have to use propyl magnesium bromide again. So propyl magnesium bromide, I'll have to stretch my retrosynthesis arrow a little bit there. And if I used propyl magnesium bromide, well, what would be the aldehyde I'd start out with? It would only have 1 carbon atom in it. So it would be this. This is formaldehyde. And if you've studied biology, you're definitely familiar with formaldehyde. So in that case, I would treat this with step 1, propyl magnesium bromide. And then in the second step, I would treat it with water. Before we move on and take a look at another problem, I just want to address one thing quickly here. When I talk about these Grignard reagents, like propyl magnesium bromide, you could also use propyl magnesium chloride, right? It would do the same thing. You could use, instead of methyl magnesium bromide, and I didn't look at the solutions manual, but they might use methyl magnesium chloride. Okay, either one would be perfectly acceptable. So that wasn't B, that was which one? I'm mixing up my letters here. That was C. All right, let's try D, which is another good one. So this is 12.13 D. We want to make this molecule. We have an aromatic ring. We have a methylene, a carbonyl, and then we have an ethyl group. All right. So for this one, I would say the best way to make this would be, did I draw it as a carbonyl when I meant to draw an alcohol? Oh, I'm losing it. There we go. Here we have a secondary alcohol. So if we want to start with an aldehyde, alcohol, come on, there we go. Well, if I think about this in terms of retrosynthesis, if I was to start with ethyl magnesium bromide, then what would my starting material look like? It would look like this. I'd have my aromatic ring, my methylene, and I'd have this aldehyde like this. So what does that mean? I'd start out with, and I'm kind of running out of space, so I'll start down here. I'd start with this aldehyde, like that. I treat it in step 1 with ethyl. I'll draw ethyl magnesium bromide. And then in the second step, I'll treat it with water. You could even practice the mechanism if you want, just for fun. You know, we could do it like this. We could say, okay, we have ethyl magnesium bromide, like that. My carbanion is going to come in here. I'm going to end up making an alkoxide, like this. There we go. There's my ethyl group. And then in the second step, I'm going to treat it with water, like that. The alkoxide is going to abstract a proton, and we're going to end up with our desired product, which is that secondary alcohol. And there you have it, folks, just like that. Let's try one more, 12.13E. 12.13, and this is E. This one's kind of a longer one because there's more than one way, more than 2 ways to do this one. All right, I'll just kind of go over this one a little bit quicker this time, but here we have a tertiary alcohol. A tertiary alcohol. We could think about this in terms of retrosynthesis. If we wanted to add this ethyl group, right? If we wanted to add the ethyl group, then we'd want to start with 1, 2, 3, 4, 5, 6, like this. We'd want to start with this ketone, right? If you count up the total number of carbons, we have 1, 2, 3, 4, 5, 6, 7, 8, right? So here I only have 6, so that makes sense. So that would be using ethyl magnesium bromide. In terms of retrosynthesis, if we wanted to add just methyl magnesium bromide, okay, what would I have as my starting material then? Then I'd have 1, 2, 3, 4, 5, 6, 7. So I'd have this ketone as my starting material. Again, that's if I wanted to use methyl magnesium bromide. And then if I wanted to add all 4 of these carbons here, okay, then for that I'd need 1, 2, 3, 4. I need 4 carbons. So 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. Yep, that looks good. So I would need 1, 2, 3, 4, and I would need this as my starting material if I wanted to use butyl magnesium bromide. Okay, give me a thumbs up if you follow me on the rationale of how to choose the appropriate Grignard reagent to make an alcohol from an aldehyde or a ketone. Does everybody follow me on that? Are there any questions? Good. Thanks, Skylar. Okay, great. Good. So again, you know, and I'll just kind of go over it quickly here. If we were to treat this in step 1 with our ethyl magnesium bromide, followed by treatment with water, we'd end up with our product. Here, if we were to treat this with methyl magnesium bromide, followed by water, we'd end up with the exact same product. And then the third way would be to start with this compound. This is butanone. I'd treat this with butyl magnesium bromide. And then in the second step, I'd treat that with water, and I'd still end up with my product. So 3 different ways to make this tertiary alcohol. Kind of interesting. Well, something that's interesting about those Grignard reagents was that they'll react with water, won't they? Right? I told you that, let's say you had methyl magnesium bromide. I'll draw it out here. If you have methyl magnesium bromide, okay, if you have that beautiful reagent, and you can buy that from a chemical supplier, you can order it from them. Let's say it's in a solution of diethyl ether. If you expose that to water, and I mean any water, just water from the atmosphere, what did we say would happen? It's going to rip off that proton, and you're going to get it converted completely. You'd end up with methane, which is a gas, so it would go up the smokestack, right? And then you'd end up with the hydroxide ion. You'd still have your MgBr plus. So there, you've ruined your Grignard, right, by treating it with water. Well, what if we had an alcohol, right? What if you tried to do the same thing and you tried to use an alcohol solvent instead of an ether? If you replaced the water with an alcohol, well, let's try that. If you were to replace this with just, methanol, let's say, what's going to happen? The exact same thing is going to happen, right? Instead of methane, in this case, you'd end up with ethane. Oops, my eraser. You'd end up with ethane. But either way, you'd ruin your Grignard, right? Sorry, did I draw methane? I meant methane. Sorry, my mistake. Mr. Deanne is tired. There we go. And methoxide is what I meant to draw. Anyhow, but either way, you ruin your Grignard. So that's not very helpful. Now, what would happen if you had a bifunctional compound, a compound that has more than one functional group? And what if one of those functional groups happens to be an alcohol? Well, you can guess that we're going to address that exact question right now. Let's say you had this compound here. It's got an alkyl halide in it right here, but it also has an alcohol. If you tried to take this compound and treat it with magnesium to make the Grignard reagent, it says right here, hypothetical Grignard reagent. Why is it hypothetical? Hypothetical because you can't make it. This cannot exist. Why can that not exist? Because you could draw it like this, 1, 2, 3, 4, like this. You could draw it like this carbanion, and then you have your BrMg plus over here. Well, that carbanion is going to rip off this proton, right? And then you're just going to destroy the Grignard reagent. It's not going to happen. Okay. So the question is there something that we could do to avoid this occurring? Is there some way that we could avoid that from happening, right? So that we could do this kind of reaction and we could make this diol. Is there a way? And the answer is yes, there absolutely is a way. Okay. And again, the reason why we can't do it in this way is because alcohol can act as an acid. And so alcohols and Grignard reagents are incompatible. They just don't mix. Okay, so what we're going to do is we're going to discuss what's called protection. Okay, protection of an alcohol. And when we protect the alcohol, what we're essentially doing is we're masking its functionality, or we're masking its ability to donate a proton. And that way we can make a Grignard reagent and we can protect that alcohol or that hydroxyl group, and then we can reveal it later on. Let me show you what I mean. What if we did this hypothetical, or this isn't as hypothetical because this we can do, but let's say we tried this. What if we could take that hydroxyl and in some way we could cover it up? Right here they've covered it up with just a black box. But let's say if there's something kind of reaction that we could do to render that alcohol unreactive, then we could form the Grignard reagent, couldn't we? Right? If you treated this with magnesium, you'd end up with your black box, okay? But then you'd have MgBr, and that is something that could exist. So then that can behave as a Grignard reagent, and you can act as a nucleophile, you generate your new alcohol, and then you remove that black box. Well, how do you do that? Let me show you how you do it. You use the protecting group that's called a trimethylsilyl, or we like to abbreviate that at TMS. Like I said, organic chemists are obsessed with acronyms. So trimethylsilyl, we abbreviate it as a TMS. So what we do is we take that hydroxyl group and we convert it into what's called a silyl ether. You guys know what an ether is. So if you have ROR, that's an ether. If you replace one of those with a silicon, that has, then we call that a silyl ether. Okay, so this is the silyl ether here. So we can convert that into a trimethyl silyl ether, trimethyl because there's 3 methyl groups on the silicon, and we abbreviate that OTMS. So we have our silyl ether. So now we can make our Grignard reagent from our primary alkyl bromide here, and the TMS is not going to react at all. Now, if you're wondering, how do you do this? How do you make that silyl ether? The way that you do it is you take the alcohol and you treat it with trimethyl silyl chloride, that's this molecule here, followed by, with triethylamine. So let me write that in here. So this is triethylamine. It's just a simple amine. Then you make the silyl ether, silyl ether, okay? Plus you end up with an ammonium salt here. So this is, and it's not ammonium chloride, but this is an ammonium salt. This would be triethyl ammonium chloride is what this would be. So you end up with an ammonium, let me just write down the name. So this is triethyl ammonium chloride. Okay, so now you have your silyl ether. Well, the reaction between the silicon atom in the trimethylsilyl chloride occurs by an SN2 mechanism. And the reason why it can happen, because if you look at this, you think, well, you know, I can't do an SN2 on this, right? That's a tertiary alkyl halide. Why in the heck should I be able to do an SN2 on a tertiary, silicon halide? The reason why is because silicon is so much bigger, right? If you look at the periodic table, it goes from carbon down group 4A. Next is silicon, which is in the third period, so it's a bigger atom. And since silicon is so much bigger, it opens up the molecule to backside attack. And so you can actually get an SN2 reaction occurring, okay? Whereas here, with a carbon, you cannot get an SN2 reaction occurring. So that's what's happening in this reaction here, is you actually get an SN2 reaction occurring on the silyl chloride. Kind of interesting stuff. Then how do you remove that black box? How do you remove that silyl ether? Well, the TMS ether can be removed, or the TMS group, I should say, can be removed in a couple of different ways. You can either use dilute aqueous acid, so we'll just call this aqueous acid, that's H3O plus, or by treatment with fluoride. Now, where do we get fluoride? Where do we get fluoride ions from? Well, usually to get our fluoride ions, we use what's called TBAF, or tributyl ammonium fluoride. That's where we get our fluoride ions from. So now we've basically developed, through the lecture here, we've kind of gone through all the steps that would be necessary to do a protection or the masking of an alcohol, followed by the formation of our Grignard, followed by the Grignard reaction itself, and then the deprotection or the unmasking of the alcohol functionality. So here's the overall process. You would take that bifunctional compound, right? You've got your alkyl bromide, you've got your alcohol. First, you need to protect that alcohol. You treat it with what? Trimethylsilyl chloride and triethylamine, and you end up making what? The silyl ether. The silyl ether is going to be impervious to, first, the formation of the Grignard reagent, second, the Grignard reaction, and third, the addition of water to make the alcohol. So we've done a wonderful Grignard process here to make this tertiary alcohol, but now we want to remove the silyl ether. How are we going to do that? Just by treatment with TBAF, right? And you could also use or dilute aqueous acid to do it there. So that's the whole process. It's pretty steppy, isn't it? Right? Not only do you, if you wanted to, or if you could do the reaction without the protection, you would avoid these two steps. But let me tell you something about organic chemistry. Number one, this isn't the last time you're going to see protecting groups come up in organic chemistry too. And so that was number one. And number two, there is an entire book, which is like a Bible for most organic chemists, written by Theodora Green. And I forget the person's first name, the Woods, but I think it's Green and Woods. You could Google it if you want, but Green and Woods. Okay, I'm not sure how to spell Woods. Is there umlauts in that? I don't know. But anyhow, in Green and Woods, this is a book that is just devoted to protecting groups. And most organic chemists will have a copy of that textbook on their, in their desk or somewhere in their office, because there are so many protecting groups out there nowadays. Now, obviously, we were only going to learn a few over the course of organic chemistry too, but there are many different protecting groups out there available at the disposal of organic chemists nowadays. Well, with all that in mind, let's see if we could solve a problem where we have to use a protecting group. It says, identify the reagents that you would use to achieve this transformation. Well, look, how many carbons are we adding? Here we have 6, 7 carbons. Here we have 6, 7, 8, 9, 10. All right, so we're adding 3 carbons overall, aren't we? And hopefully you can tell by now that the 3 carbons we're adding are this carbon, and this carbon. Right, we're also making this alcohol. But since we have an aryl bromide here, we could convert that to a Grignard reagent. However, there's a big problem. So big, I got to use a red pen. If we were to just treat that with magnesium in hopes of making this compound, MgBr, and I'm going to draw it with the bond. If you want to draw it as ionic, go ahead. But that's not going to happen, is it? Right? This is not going to work. Why? Because a Grignard reagent is not compatible with an alcohol. What does that tell you? It tells me that the first thing I need to do is protect that alcohol. I've got to protect that hydroxyl group. Now, before we get into that, I want to think about the actual Grignard reaction itself. Right? In terms of retrosynthesis, what is my electrophile going to be if I make that Grignard reaction or Grignard reagent that I was talking about? Right? If I could make the Grignard reagent with my magnesium in here, if I want to add these 3 carbons, that means I'm going to need to have a 3-carbon ketone, which can act as my electrophile. So let's start by first treating it with magnesium, which makes our, first by protecting it. So TMS, that's trimethyl chloride, and triethylamine. I'm getting too eager here to get the synthesis going. There we go. So now we've protected our alcohol. We have our OTMS. Make sure to draw the molecule in such a way that the sulfur, the silicon, the S, is next to the oxygen, like that. Okay, because that's the actual atom that's attached to the oxygen. So now we have our silyl ether. So this is the silyl ether. Okay, next we're going to make the Grignard reagent. So we're going to treat it with magnesium. And then we're going to make this guy. So MgBr. Still got our silyl ether over here. Now again, you can treat that bond as if it's ionic, can't you? Right? You can treat that like this. So in the next step, we're going to treat this with our electrophile. We get in the first step that nucleophilic attack, right, which makes this molecule. And then in order to get us to our final product, the first step, we're going to treat it with H2O to convert this into the alcohol. And then, and I should have left that out, but anyhow, there we go. First, we're going to treat it with water. And then in the second step, we're going to treat it with TBAF. And that is going to remove the silyl ether, TBAF, like that. So overall, how many steps do we have? We have 1, 2, 3, 4, and 5. So again, to recap, step 1 is trimethylsilyl chloride and triethylamine to make our silyl ether. Step 2 is make the Grignard reagent. Step 3 is treat it with the electrophile. In this case, it's acetone. Step 4 is to treat it with water. And then step 5 is to treat it with TBAF as our source of fluoride ions to do the deprotection. And there we have it. Give me a thumbs up if you follow me on that question. Really important that you know how to do this type of synthesis. So this one is what? 5 steps. Does everybody follow me on that one? All right. Thanks, Jenna. Thanks, Skylar. Good. Awesome. Awesome. It's not simple. It's important, but it's not simple, is it? All right. Let's just see where we are. Let's move on from there and let's talk about some other reactions of alcohols. The good news is that we're going to see some reactions in section 12.9 that we've seen before. And also, we're going to end up skipping section 12.8. So I'm not going to quiz you on section 12.8 at all. If you want to take a look at that, it's called the preparation of phenols feel free to do that, but we're going to skip it. So this first reaction is one that we would have learned all the way back in about chapter 7 in Organic Chemistry 1, taking a tertiary alcohol, like this one right here. This is terbutanol, treating it with a strong acid like HBr, converting the hydroxyl into a good leaving group, which would leave to form a tertiary carbocation. Then we have a nucleophilic attack of the bromide. What kind of reaction is that? That's just an SN1 reaction with a tertiary alcohol, isn't it? So again, that's something that we've already seen before. Now, what about a primary or secondary alcohol? The reaction doesn't occur via an SN1 mechanism, does it? It's going to occur via an SN2 mechanism if we're using a primary or secondary alcohol. Same type of mechanism, but now we have two steps that occur simultaneously, right? We have our proton transfer, we have the conversion of the alcohol into a good leaving group, and then we have the two steps occurring at the same time, the nucleophilic attack, right, followed by the loss of the leaving group. So that's an SN2 process. Again, these are reactions that we saw in Organic Chemistry 1. So what have we got? We've got two different ways that we can take, or two ways that we can either take a tertiary alcohol, convert it to an alkyl halide, or a primary and secondary alcohol and convert those to an alkyl halide. Well, what if you wanted to make an alkyl chloride, a primary alkyl chloride, instead of an alkyl bromide? In order to do that, since HCl is a weaker acid than HBr, you actually have to spruce up the conditions a little bit. You have to use zinc chloride. And zinc chloride behaves as a Lewis acid. What's a Lewis acid? It's an electron acceptor. So what the zinc chloride does is some of the electron density from the lone pairs on the oxygen gets dumped into that zinc, which renders the carbon more electrophilic, right? Because the oxygen now has a positive charge on it, so that renders this carbon even more susceptible to nucleophilic attack, so the chloride can come in, behave as a nucleophile. So these are a set of conditions that you have to know. If you want to take a primary alcohol and convert it to a primary alkyl chloride, instead of just using HCl, you have to use HCl and zinc chloride together. Now remember that the hydroxyl group can be converted into a good leaving group using a tosyl, T-O-S-Y-L, right? Tosyl, which was a toluene sulfonyl, right? And we spent some time talking about the toluene sulfonyl group. So it looks like this. So you have tosyl chloride, right? And this is just a little bit of a review from Organic Chemistry 1. This is TSCl, tosyl chloride. And then if you take a primary or a secondary alcohol, we treat it with tosyl chloride and pyridine. And pyridine is just a benzene where we replace one of the carbons with a nitrogen. So that's pyridine, which we abbreviate PYR. Well, again, if you take that alcohol and you treat it with tosyl chloride and pyridine together, you make a tosylate, right? The tosylate is a good leaving group. Why? Because it's the conjugate base of a strong acid, which would be toluene sulfonic acid. Well, now that you've got that converted to a good leaving group, if you attack that with the appropriate halide, as is shown here, you can do an SN2 reaction, but notice that it proceeds with inversion of configuration. Notice that the first step, there was retention of configuration, right? Both of these are wedges pointing out, but now we have a dash going in the back. So we get inversion of configuration because this is an SN2 process. What are some other reactions we could use to convert a primary alcohol to a primary alkyl chloride or a primary alkyl bromide? These are a couple of brand new reactions. So the first one is if we take a primary alcohol and we treat it with SOCl2 and pyridine. SOCl2, that's called thionyl chloride. You can draw the Lewis structure of thionyl chloride. It looks like this. And that's the Lewis structure you should be able to draw. So thionyl chloride and pyridine. And another reaction that you could use to make a primary alkyl bromide is phosphorus tribromide. phosphorus tribromide. I worked with a guy in the industry that, in fact, the first person I ever shared an office with, phosphorus tribromide was his favorite reagent. He tried to use it for everything. He'd always be like, PBr3, you get the PBr3. I'm going to use that. We're going to try that for this reaction. Anyhow, and also every student should be able to draw the Lewis structure of phosphorus tribromide. Okay, that's just, a little bit of Gen Chem 1. There we go. All right. So these are two brand new reactions. Now, how would you remember these? Well, you could either, do the practice problems in the back of the book, which I highly recommend doing. You could make 3x5 cards. You could write them out repeatedly. Either way, you've got to come up with some kind of strategy to know these reactions. The conversion of a primary alcohol, primary or secondary alcohol, but here they just have a primary, and to convert it to an alkyl chloride using thionyl chloride and pyridine. Again, you could also use HCl and zinc chloride. That will work too. Or you can use phosphorus tribromide in order to do that. Or you go back here, we saw that you could also do the same thing just by treatment with HBr. So you see how organic chemists almost always have more than one way of doing a transformation. And you got to keep all these different transformations organized in your mind. Now, the mechanism for thionyl chloride, the mechanism for the conversion of a primary alcohol to a primary alkyl chloride using thionyl chloride, I will not ask this mechanism. So let me write it in here. Will not ask you this mechanism. However, like I said earlier today, if you think about any class that you really enjoy, it's always going to be a class that you understand the most. And so I recommend taking a look at this mechanism. It is in our book for a reason. However, it's not tested by the ACS, and so I don't ask my students questions about this mechanism. But I always have somebody who's got an inquiring mind and wants to know these types of mechanisms, and it's shown here. What's cool about this mechanism is you give off sulfur dioxide, which is a gas, and so you can imagine that this is an irreversible reaction based off of Le Chatelier's principle, right? Because the gas isn't coming back in the reaction mixture. Likewise, our textbook also shows the mechanism for the conversion of a primary alcohol to a primary alkyl bromide using phosphorus tribromide. Now, this mechanism is a lot simpler. There's only 3 arrows, right? Much simpler. And you can't see the entire thing. You can't see the byproduct here. Can you? There you go. HOPBr2. So I can write it over here so you can see it a little better. HOPBr2. Anyhow, again, this is another mechanism that I will not ask. Will not ask. But if you think about these two mechanisms, if you, good students are always looking for different ways to draw parallels between mechanisms, and I do the same thing. You notice what happens in both of these mechanisms? Same darn thing, right? All you do is convert the hydroxyl into a good leaving group with thionyl chloride. Same thing here. You just convert it into a good leaving group. You end up making the primary alkyl bromide, and you also produce dibromophosphorus acid. Okay, there you go. All right, what is another reaction of an alcohol that we saw? This is one of my favorites. It's a bit of a dark horse in organic chemistry one, but it does come up now and again. When we take an alcohol and we treat it with a strong acid, what are we going to get? Well, I'll tell you right now, you're going to get the Zaitsev alkene. What's the Zaitsev alkene? It's the more substituted alkene. Now, here we're taking terbutanol and we're treating it with concentrated sulfuric acid, so there's only one possibility, right? There's only one. There's no Zaitsev or Hoffman here. There's only one possible alkene that you can get. So you can imagine that's a really good reaction, right? What's the mechanism by which this type of elimination occurs? It's an SN1 reaction. First, what do? You convert that hydroxyl into what? A good leaving group by protonating it, right? Once you protonate it, it gets lost as water. Well, water is the conjugate base of hydronium, which is a strong acid, and so water is a great leaving group. Then we do a proton transfer at the end to produce the alkene. Very good reaction, very powerful reaction. What's nice about this reaction is that you're only using a catalytic amount of H+, only a catalytic amount. And so this reaction has very good atom economy. When we think about, wanting to try to do organic chemistry as green as possible without creating much waste. Well, remember, and this is just a slide saying what I just told you, is that if there's a possibility of making a Zaitsev and a Hoffman alkene, and if you're confused about what that is, the Zaitsev is simply the more substituted alkene, right? This is a tri-substituted alkene versus the Hoffman. I can never remember how to spell Hoffman, if it's one N or two, anyhow. Right, this is a di-substituted alkene. So when you do this reaction, and it's one of my favorite reactions, when you treat it with that strong acid, okay, and you just heat it up, you're always going to make the Zaitsev as the major product, okay? It's going to be the thermodynamic product, right? And you're heating it, so there you go. The less substituted alkene could only be favored. The only way you could make this one the major alkene is if you did an E2 elimination using a big bulky base. Now, I'm going to look ahead of my slides. I don't think I have that written down anywhere, but let me just show you. And I know you already know how to do it, but I just want to review with you quickly here. If you were to take this tertiary alcohol and first treat it with tosyl chloride and pyridine, then you'd make the tosylate. Okay, don't get that confused with the silyl ether. That's something completely different. Then if you treated that with potassium T-butoxide, right, that would abstract this proton, right, that beta proton. And then you'd end up with this compound, which is called methylene cyclohexane. Okay, that would be the major product. All right, here we go. If the alcohol is converted into a better leaving group, then a strong base can be used to promote the E2. I just showed you how to do that. E2 are generally preferred over E1 reactions. E2s aren't susceptible to rearrangements, and the regioselectivity can be controlled. And we saw that a lot in the alkenes chapter, right? This is nothing new to us. That is something that we looked at, almost Avogadro's number of times back in our alkenes chapter. Well, with all that spinach in mind, and there's quite a bit of information there, let's see if we can find some reagents that we could use to affect these transformations. Well, this first one here, I want to take this secondary alcohol. It's on a wedge, and I want to convert it to this secondary alkyl bromide, and it's on a dash. So I'm inverting the stereochemistry. Could anybody give me an idea where I might start to do this type of transformation? There must be some kind of substitution involved because I'm inverting the stereocenter. Yeah, thanks, Skylar. Absolutely. I'm surprised that you came up with that first, right? Great. Gilbert, definitely on the right track too. Excellent. Both of you are right. If you were to treat this with just PBr3, I'm very glad that you noticed that this reaction will proceed with inversion of configuration. I want to back up and show you something. Okay, and I saved this for a reason. Where's my mechanism? Right here. Okay, the PBr3 mechanism, look, after you convert it to a good leaving group, look what happens. When the bromide comes in and acts as a nucleophile, it's going to attack this carbon here. This is an SN2 reaction. So that means if this is a stereocenter, and it's not here, obviously, but if it was a stereocenter, this would occur with inversion of configuration, wouldn't it? Absolutely. Okay. Again, I know this isn't a chiral carbon. I'm fully aware of that. But if it was, it would occur with inversion of configuration. Why? Because that's an SN2 reaction. Great. Excellent work, Skylar. So that would be a perfect way to do that, PBr3. Now, Gilbert's on the other path. He said, well, what if you treated that with tosyl chloride first, tosyl chloride and pyridine? Then you'd convert this into a good leaving group, right? You'd end up making this compound. So you'd still have your wedge intact. But then if you took that and in the second step, you treated that with sodium bromide, NaBr, right? Then the bromide is going to come in, act as a nucleophile, but that's an SN2. And so that would proceed with inversion of configuration. Okay, now that's a really wacky way of showing the reaction. So what I'm going to do is I'm just going to erase all this. And yeah, let's delete that. So first step would be toluene sulfonyl chloride and pyridine, or tosyl chloride and pyridine. And then the second step would just be sodium bromide. And since it's an SN2 reaction, you'd want to use a polar aprotic solvent. If you want to write one, you can. Acetone, acetonitrile, DMSO, they're all good. Anyhow, let's take a look at the next one. Here we've got a tertiary alcohol. All right, we're starting it with a tertiary alcohol, and we want to convert that into a tertiary alkyl bromide. Could anybody tell me what they think might be the easiest way to do this, or what they think might be a good way? And there's a couple of ways that we would know how to do this. What was the first reaction that we looked at in this section, in section 12.9? If you don't remember, I could take a step back here and help refresh your memory if I can find it. Right, the first reaction that we looked at exactly was taking a tertiary alcohol and treating it with HBr to make a tertiary alkyl halide. Absolutely, thanks. My students are on the ball. Yes, so we could just use HBr. That would work, yeah. I'd say that PBr3 would work here as well, okay? So we'll put here, or PBr3 would also work. Let me say, or PBr3. Next one is pretty similar, or it's, you know, in the same vein as the first one. I'm just thinking out loud here, I'm thinking to myself. For the second, or for C. Well, I'd say one option for this one to convert this secondary alcohol into this secondary alkyl halide and to do or to allow the inversion of configuration to occur would be just to treat it with thionyl chloride. Let me prove it to you. If you go back to the mechanism where we saw the thionyl chloride reaction to convert the alcohol into the alkyl chloride, after you've converted it into a good leaving group, what happens? This step here, this is an SN2 reaction, right? You have the nucleophilic attack here, and then you lose all this spinach at the same time. Okay, you lose the sulfur dioxide and the chloride. So that's an SN2, so that would occur with inversion of configuration. So thionyl chloride would be one option. Another option would be to do, you know, kind of a long way, which would be to what? First, convert it into a tosylate, so tosyl chloride and pyridine, and then you'd use sodium chloride. Okay, that would work as well. All right, and then the last one, if we want to take that secondary alcohol and convert it into the alkyl bromide, and we want the inversion of configuration to occur, or we're allowing that to occur, we could just use phosphorus tribromide again. Next one, it says predict the products for this transformation. We have this unsymmetrical tertiary alcohol, and we're treating it with concentrated sulfuric acid, and we're heating it up. What we're going to do is we're going to end up with both the Zaitsev product and the Hoffman product. However, the Zaitsev product will be the alkene that's formed in the greater amount. So, I mean, there's two types of beta protons, right? I've got these beta protons in red, and I've got these beta protons in blue. If I remove the beta proton in blue, I would make this as my alkene. This is the Zaitsev. This would be the major product. And if I abstract the proton in red, I would end up with this, which would be the minor product. Okay, remember the major is the Zaitsev. It's the more substituted of the two. And then this one would be the Hoffman. All right, again, if you're wondering, you know, how do you know it's Zaitsev? How do you know it's Hoffman? If you look at the two carbons in the double bond, these two carbons are attached to 1, 2, 3 carbons overall. So we call that a tri-substituted alkene. This alkene, you look at the two carbons, oops, like this, they're attached to 1, 2 carbons overall. So that's a di-substituted alkene. So tri-substituted is more stable then a di-substituted alkene, and so that would be the major product, which is driven by thermodynamics again, because this reaction is heated.